This is lesson 18 on the conditional proof. So we've learned how to write proofs for valid arguments. However, there are two more rules that I want you to learn so that you can use them in writing proofs for valid arguments. We'll learn those in this lesson and the next one. In this lesson, we'll learn the conditional proof. Let's start by proving this particular argument. If you can run a 4-minute mile, then you are a world-class athlete. Therefore, if you can run a 4-minute mile and you are a teenager, then you are a world-class athlete. Seems pretty obvious that that argument is valid, right? Let's prove it. The argument is symbolized like so. If F, then W. Therefore, if F and T, then W. For step 2, we immediately start with addition, because we have a missing constant that's in the antecedent of a conditional. More than that, we start by adding the negation of that constant, not t, as we learned to do in the last assignment. Then we need to get that t, that not t, onto the left side of the if then, so we can do a commutation around the or. Now we can turn it into an if then by the rule of material implication. The negation disappears in the equivalence as well, of course, which is handy. Okay. Now we can make it look like the conclusion by doing an exportation, moving the parentheses and changing that first if then into an and. If T and F, then W. Finally, we do a commutation to get the proper antecedent and consequent order and QED. Okay, that's actually a pretty complicated proof. The validity of the argument is much more obvious than the proof itself. Why is that? Why is it so obvious even though the proof is pretty difficult? Well, here's one thing I think we can consider. We tend to think of if P then Q as a contained argument. P, therefore Q. So if we think that way, the argument looks something more like this. If you can run a 4-minute mile, then you are a world-class athlete. You can run a 4-minute mile and you are a teenager, thus you are a world-class athlete. Well, this argument is much easier to prove. If F, then W, F and T, therefore W. All we do to get the W from there is simplify the F and T into F. Then we can do modus ponens. If F, then W, F, therefore W. There it is, we're done with this argument, QED. Much easier to prove and basically the same idea, just turning the antecedent and consequent into a premise and conclusion. So the conditional proof allows us to make that sort of change, not in exactly the same way, but the same idea is behind it, and this is how it's done. Conditional proof, CP, allows us to assume the antecedent of the conditional. From the antecedent, we deduce the consequent. We then conclude the entire conditional. Our example would work like this. Up there. If F, then W, therefore, if F and T, then W. This was pretty difficult to show without the conditional proof, but watch this. What we do is assume the antecedent. The antecedent is F and T, and we label that CPA, which stands for Conditional Proof Assumption. So we assume F and T, and now we try to deduce the consequent. In this case, we try to deduce W. Well, how can I get W out of all that? Well, just like we did before, we simplify the F and T to an F. And then we do modus ponens to get the W. Now, we assume the antecedent, we deduce the consequent. The conditional proof allows us then to conclude the entire conditional for step 5. If antecedent, then consequent. If F and T, then W. And our justification is 2 through 4 CP, conditional proof. The 2 being the number where we made the conditional proof assumption, and the last number being 4, where we deduced the consequent. And we say steps 2 through 4 because we've used that entire process to conclude the conditional proof, and that's what we were trying to prove. So remember that CPA stands for conditional proof assumption here, and that's how it works. Let's do another proof, one without CP and one with CP, to show you that although you can do without it, it's much easier to work with the conditional proof. So here's the argument. If P then Q or R, if P then not Q, therefore if P then R. Now this is a pretty difficult proof. It's not easy to see where I should start in order to conclude if P then R. We see that it's probably got to be built around a hypothetical syllogism because we do have 3 conditional statements, but how we get that middle term to match is pretty tricky. It's going to work something like this though. So we're going to start by doing a double negation on the Q. And the reason we do that is we now have a not something or something that we can then use our favorite material implication to turn into an if then. So do that next. If P then, if not Q then R. Now we have something that's set up for exportation. If P then, if not Q then R turns into if P and not Q then R. And now we're closer to our hypothetical syllogism. We have to get this not Q involved. The way we do that is by the absorption. We turn if P then not Q into if P then P and not Q. Now the middle parts match and we can conclude if P then R by hypothetical syllogism QED, and we're done. It's only 7 steps, but I think it's actually pretty difficult, and it would be hard to see the first time you're doing this proof. But now, let's do it with a conditional proof. So same sort of thing. If P then Q or R, if P then not Q, therefore if P then R. With the conditional proof, we assume the antecedent. In this case, we're trying to prove if P then R, so we assume P with our conditional proof assumption for step 3. Now, from this and from the other premises, we try to deduce the consequent. We try to deduce R. How can I get an R out of all that? Well, look at 1 and 3. If P then Q or R, P therefore Q or R by modus ponens. Next we have if P then not Q, P therefore not Q by modus ponens again. Now I have Q or R and not Q. So next step, I can deduce that R from the disjunctive syllogism. And notice what I've done. I've assumed the antecedent and I've deduced the consequent now. The conditional proof allows me to conclude the entire conditional. If P then R, 3 through 6, CP. I assume P and I get R, therefore I can conclude if P then R by the conditional proof. 3 being the number of the assumption, where we assume the antecedent, 6 being the number where we deduced the consequent. It's about the same length, but I think this proof is much easier to see than the other proof. And of course, it's perfectly appropriate and valid to use the conditional proof assumption to track reasoning. A couple notes that you should recognize though, before you begin to use the conditional proof at home on your own. First of all, you should know that you don't necessarily have to have a conditional in the conclusion in order to use a conditional proof. All you need is a conditional somewhere. It could be in the middle of a longer proof. Let's have an example of that. If P then Q, if Q then P and R, therefore P if and only if Q. Notice my conclusion is not a conditional, but we know that P if and only if Q is logically equivalent to if P then Q and if Q then P. That means I need an if Q then P, as I already have an if P then Q in the first premise. How can I get an if Q then P? Well, I'm going to use a conditional proof. I'm going to assume the Q from the conditional proof assumption and then deduce the P. So look at what I have. If Q then P and R, Q therefore P and R by modus ponens. Then I can just simplify that P and R to P by simplification. Now I've assumed Q and I've deduced P, and that means I can conclude if Q then P by the conditional proof. Now I'm not necessarily done. I can just keep going with the proof. Just because I've used the conditional proof doesn't mean I have to stop. Now I have if P then Q in step 1, if Q then P in step 6, and I can do a conjunction between those two by steps 1, 6 conjunction. Then by the rule of material equivalence, I can conclude P if and only if Q. I've got the if Q then P that I needed by assuming the conditional proof. By assuming the antecedent, deducing the consequent, concluding the entire conditional. So the conclusion itself doesn't have to be the conditional. That's the whole point of that. You just have to use a conditional somewhere in the proof when you use the conditional proof. Now, the conditional proof assumption may only be made when using the conditional proof. You can't make the conditional proof assumption and then stop without using the conditional proof. Doing that would allow you to conclude invalid arguments. That's bad. So for example, if you have if P then Q, therefore P or R, you cannot prove R in this way. P by CPA, P or R by addition. You've made the conditional proof assumption, but you haven't proved the conditional, and so that's an error. And in fact, you could do a shorter truth table to show that that disgusting argument is invalid. So you can only make the conditional proof assumption if somewhere in the proof you are going to conclude with a conditional proof. Also, a huge rule related to that. The conditional proof is self-contained. You may not select one step out of the middle of a CP to use later in a proof. So for example, take a look at this proof for the if F then W, therefore if F and T then W. Look at that up there. This is a pretty good argument the way we're looking at it right now, but What we can't do next is this, F and W by conjunction. That's in fact invalid. If F, then W, therefore F and W is invalid, and that shows you can't take parts out of the middle of a conditional proof and use those individual steps after you've concluded the conditional proof. The conditional proof is sort of its own self-contained unit, as I said. We can draw some brackets up there to show you what you can't grab piecemeal. You can pull stuff before the conditional proof and after. You could have pulled if, F, then W. But once you've made the conditional proof assumption, that all has to be self-contained, and you can't pull any pieces out of it later in the proof. So, in summary, the conditional proof can be used when a conditional occurs somewhere in a proof. The antecedent of a conditional is assumed, justified as CPA. Then the consequent is deduced using that assumed antecedent and the other premises. Then the steps involved in this are used to conclude the entire conditional, put together, justified as CP. The first number in the conditional proof justification is where you assumed the antecedent, and then you use a dash, and then the second number is where you deduced the consequent. So let's take a look at exercise 18 next. Even though you could solve all of these arguments without the conditional proof, I want you to use the conditional proof every time. In number 1, you're going to assume A with conditional proof assumption in line 2, and then try to deduce B from the premises you have, and that new assumption, of course. And you will conclude if A then B with the conditional proof in the last line. In 2, you assume D and deduce E or F so that you can conclude that conditional in the last line. In problem 3, assuming G, deduce H and I to conclude if G then H and I. In number 4, make sure you assume the entire antecedent, the entire J or L when you're doing the conditional proof. Notice in number 5, we don't have a conditional in the conclusion. We have a not M or not P. But you should also know that not M or not P is equivalent to a conditional. So figure out what that conditional is, and then assume the antecedent of that conditional. You're not going to assume not M with a conditional proof. You'll be assuming something else. With number 6, you assume Q and you try to deduce T. 7 and 8 are a bit unusual. I'm sure you've noticed with a tinge of disappointment, that they're really short. U, therefore, if W, then W. Without the conditional proof, that's actually a very complicated argument. Nothing you couldn't do though, of course. You solved one very similar to that in the last assignment. But here, you assume the antecedent and deduce the consequent. Notice that when you assume the antecedent, you've already deduced the consequent. And so in your hyphenated justification for the conditional proof on this one, the line numbers will in fact be the same number. That doesn't often happen, so enjoy it. 8 perhaps is even stranger. You assume the antecedent y, you try to deduce the consequent, but you already have the consequent x. So here, the line numbers are actually going to go in reverse numerical order on the conditional proof. Finally, on number 9, assume the antecedent, deduce the consequent. This one gets a little longer, but it's good practice for a longer argument using the conditional proof. Knock yourselves out. On the wall behind me, you can see the 50 adorable fallacies from the amazing Dr. Ransom's Bestiary of Adorable Fallacies. This is the informal fallacy book that all of your family is going to love reading together. Second book I wanted to show you is a book written just for classical homeschoolers, Classical Me, Classical Thee, Squander Not Thine Education. This book explains why you have to do all the classes you're trying to do. So please remember to subscribe and hit the bell. You can check the links below in the description for these 2 books and anything else from Logos Press. Thanks for watching.